Greetings. I'm Joe French, and I'm coming to you from my classroom in Mount Pleasant, Utah. And this is topic 2.3 of the AP Calculus curriculum, estimating derivatives of a function at a point. And we'll go over some examples. So when estimating derivatives at a point, there are three possible situations that we could find ourselves in. The first is estimating a derivative or an instantaneous rate of change from a graph. To do this, we'll sketch a tangent line and estimate the slope of the line, the best guess. Here we have an example, this graph, and we've got this point, this purple dot here, we'll call C, and we want to know the derivative here. So I'm going to sketch a tangent line that seems to simulate what the curve is doing at that point. Once I've sketched that line, then I can calculate a rise over run. So I'll figure out how much I rose over how much I ran. And it seems to me that we've run just a little bit over 1 unit. And here we've gone up about 5 units. So my change in y over my change in x is 5 over 1. So we would say our estimate for our derivative in this case would be about 5. When given a table, then our choice is to use the two closest surrounding points and calculate the average rate of change between the points. Again, we're not going to be able to calculate an instantaneous rate of change if all we have are discrete points in our table. So in this case, I'm being asked to estimate the derivative of g at 2.5. Well, I don't have 2.5 as an x value in my table. All I have are 2 and 3, the 2 points closest to 2.5 on either side. So I'm going to use my slope equation, y2 minus y1 over x2 minus x1. My y2 is 8, my y1 is 5, and my x's are 3 and 2. So my ratio would be 3 over 1. Sorry for the messy handwriting. And I would get an estimate for my instantaneous rate of change by using my average rate of change and get 3. We'd say that this graph is changing at about a rate of 3 units to 1 unit at 2.5. Let's look at some other ways we might be asked to find a derivative at a point. For instance, from an equation. In this case, we get to use technology. Our calculators have a derivative function. And for the AP, we always want to give our answers to 3 decimal places. We're not using scientific notation or significant figures. For the AP, they always expect 3 decimal place accuracy. So let's look at a question here. This function, f of x equals 3/4 x cubed minus 2x squared plus x to the 4/3 minus sine of x. And we want to know the value of the derivative when x equals 1. Here's where our calculators are such wonderful tools. In our calculator, I like to put my equation, the equation in question, into my y equals screen because it allows me to do lots of different things with the equation itself once I have it stored in the calculator. So here I've stored it in the calculator. 3/4 x cubed minus 2x squared plus x to the 4/3 minus sine of x. The next thing I do is I go back to my home screen and I call up my derivative function, which I can find in my math menu. And down here, option 8, where it says nderiv, that's my math equation, my derivative equation. So I'm going to select number 8. And now you can see it looks very similar to our ddx derivative notation. And I'm going to take my derivative with respect to x. And then since I stored that equation in y1, I'm going to call up the y1 variable by going alpha trace. And then you can see that option 1 is the y variable y1. I'm going to select that. And then go over to the last box on the right and tell it which x value I am interested in, and that was 1. So I'm going to choose 1 and hit enter. And there's my answer, negative 0.956968. And now if I'm going to go to 3 decimal places, that means that I will round to negative 0.957. So once I've done that, I might have another question that asks me to look at various values of x. And this is why I'm extremely happy that I put my equation into y1 so I don't have to continually retype my equation to find these derivative values at different values of x. So at x equals negative 2, x equals negative 1, x equals 0, and x equals 1. If I go back to my calculator, I can go up by hitting the up arrow twice and highlight my last entry and hit enter. And now I can go back and simply change my values. We were looking at negative 2. And then I can go up again, grab it again, change to negative 1. I can see that from negative 2, where my value was 15.736, it changed to 4.376 at negative 1. I can check at 0 next. And see, oh, it looks like it's about negative 1 here at 0. So if I have checked all my values, negative 2, negative 1, 0, and 1, it looks like that at negative 2, I have the greatest slope. Here's a third example. I have a graph of a function here, and it's shown for all values between a and b. It's continuous. But the derivative exists everywhere except x equals 0. So right here, we'll talk about why the derivative doesn't exist there in the next section. And now we're curious for how many values of c, for every c between a and b, does this limit as x approaches c equal this expression, which is the average rate of change between my endpoints, change in y over change in x. This expression on the left is my derivative of the function. So what we want to do is think about, well, the average rate of change is the slope of the secant line between the 2 points. So I'd want to know what this slope is. And then I'd want to compare it to the derivative, which is the slope of the tangent line. And I don't actually need to know, to answer this question, I don't actually need to know the values. I just have to be able to visualize what that tangent line would look like and see whether it's parallel, has the same slope as this slope between the endpoints. I have created a visual, so first pause and see if you can come up with an answer. How many times does my tangent line, right now my tangent line seems to be going up, definitely not parallel, but where would that tangent line be parallel to this line between the endpoints, the secant line? So take a moment, pause, and come up with a number. How many times? Okay, I'm going to assume you paused. Let's take a look here. I've stretched out the graph a little bit so we can see a little bit better, but here it's the same graph, same boundaries, and I've drawn the line between the endpoints, and then I've drawn this line, this tangent line, that will change as we move up and down the curve. Now, as we move from right to left here, I'm looking for places where these two lines might be parallel. That looks like a place somewhere close to this, maybe right there or so. So there's one. Now I'm going to come up the curve. It's definitely not parallel anymore, but now it's starting to level off again. And it looks like there might be another place here right before it levels off. So there would be two. And then definitely not parallel, not even defined at 0. And then, oh, we've changed abruptly, and now here we come. And as the curve levels off, it looks like our tangent line's also leveling off and getting closer and closer. So it looks like there's a third place right there. And then as we come down, again, definitely not parallel, not even in the same realm. But now as we come down and come out of this bottom hump, it looks like there might be one more spot, a fourth location where the slope of the tangent line is equal to the average rate of change between A and B. So our answer here, there are 4 locations between A and B where that would match. So just to recap, 3 different situations where we might be asked to estimate a derivative at a point. From a graph, there we just sketch a tangent line and give it our best guess by measuring rise over run for our line. From a table, where we calculate our slope between the 2 points closest to the point they're asking about, one on either side. And finally, from an equation where we get to use our technology. And that ends our lesson.